Hey everyone, so welcome to this segment of Chapter 7, Thermochem, basically discussing Section 7.5 of this chapter. This is going to be related to bomb calorimetry. Okay, so uh, we talked about heat and work in the last video and how those are forms of exchanging energy within the system and the surroundings. Now we're going to expand on that a little further. So here's a recap slide, uh, basically saying how we have a pretty much complete picture of how a system exchanges energy with its surroundings. Okay, so we know that it exchanges it in the form of heat, which if it does, we can calculate and quantify the heat as mass of whatever we're looking at times the specific heat times the change in temperature of the system or the surroundings, right? Depending on what we're talking about. And we can quantify the amount of energy due to work by having it equal to the negative of an external pressure times the change in volume. Okay? So if you want to calculate Q, heat, you need to have a change in temperature. If you want to calculate work, you need a change in volume. Okay, and all of this we talked about in the last video. But now that we have a complete picture of how the system exchanges energy with its surroundings in the form of either of these two, we need to think about now how the change of internal energy, delta E, is affected by that. And remember that delta E is equal to Q plus W, right? We talked about that before. So delta E, the change in E, internal energy, is a measure of all of the energy, heat and work, exchanged with the surroundings, right? You have to take the heat and the work combined to figure out, the total energy that was exchanged. As a result of that, we can measure the change in temperature and the change in volume in a chemical reaction. Right? And then you can just sum all of those together to calculate delta E. Okay? So it's actually a lot easier to calculate only one of them, right? Because when you have both heat and work going on at the same time, it's really hard to measure both of those quantities experimentally at the same time. For reasons we don't even really need to get into. We don't need to talk about why it's hard to measure both at the same time, but obviously it's easier to measure one of the factors that contributes to energy instead of two. And if we know that heat and work both contribute to the total energy, if we could just calculate one of them and represent all of the energy as one of the terms, it makes life easier. So it turns out that the one that we calculate is heat and not work. So it would be a lot better, like it says in this point, an easier way to obtain the value of delta E for a chemical reaction is to force all of the energy change associated with a reaction to manifest itself as heat rather than work. So basically we're just trying to get delta E to equal Q and not W. Well, how's the only way that's going to happen? I mean, we can't just ignore work. And the only way we can get away with not calculating work is to not have a change in volume. So basically, if the volume stays the same, because we know how to get work, right? Work is associated with a change in volume. But if we keep the volume constant and we don't change it, the change in volume is going to equal zero. And if the change in volume is going to equal zero, then, if you substitute that in, work equals negative of an external pressure times the change in volume. If delta V is zero, then the work is zero, right? So bottom line is, if you're carrying a chemical reaction out where you keep the volume constant, right? Let's say whatever chemical reaction is happening isn't going to move the piston up and down or in any sort of direction. The volume won't change. You just kind of keep it locked in position. And you only allow the chemical reaction to perform heat, as that's the only way that energy is transferred in the form of heat, you can do that by making sure the volume doesn't change. And if that's the case, then if we know delta E, the change of internal energy of a reaction, is equal to Q plus W, if we keep the volume constant, we can say that the heat of a reaction, subscript V basically says that you're at constant volume. Okay, so the heat at constant volume plus work. And if the volume's constant, W is going to equal 0. So if W equals 0, it's really just going to be delta E of the reaction is equal to the heat evolved or given off in a chemical reaction at constant volume. Okay, so delta E of the reaction is equal to Q at constant volume. And we basically have achieved our goal of only calculating and quantifying energy for only in terms of one of the two terms, Q and W. We took W out of the equation, and now we can just quantify the amount of energy in terms of heat. So that's great. Now, how do we do that experimentally? We're going to look at that in just a second. We can measure the heat evolved in a chemical reaction using something called calorimetry. Okay? And particularly, this is going to be constant volume calorimetry. So if you're trying to measure the change in internal energy of a chemical reaction at constant volume, you can use a technique called calorimetry. And we're going to see it's basically a way to measure the thermal energy exchanged between the reaction, which we define as the system, and the surroundings. And what we're doing in calorimetry, this is the key thing, and I underlined it here, is in calorimetry, the way that you measure the thermal energy of a system, like a chemical reaction, is by observing a change in temperature of the surroundings, right? And it makes sense that the temperature would change. The surroundings' temperature would change if the system is acting on the surroundings, right? Just think about it. If you have a chemical reaction and that's your system, and it's giving off some sort of thermal energy, right, as heat, that heat is going to be transferred to the surroundings, and the temperature of the surroundings is going to change. And if we know that there's a relationship between the amount of heat that's in a system versus the surroundings, we've seen that before, you know, how we set them equal to each other, right? The amount of energy lost by one is the exact amount of energy gained by the other, right? We can figure out what the change in internal energy of the system is by figuring out what happened to the surroundings. Okay, and we wrote it here. We said the magnitude of the temperature change in the surroundings depends on the magnitude of delta E for the reaction, right? One depends on the other. And you also need to think about the heat capacity of the surroundings, right? Remember, Q equals MC delta T, but realize that we don't really have a specific heat involved here. Remember, specific heat capacity, C, is specific to one substance, right? Like water, right? There's a specific heat of water. It's 4.18. There's a specific heat of aluminum. We saw copper, all this stuff, right? But if you're looking at a calorimeter, the calorimeter is made of multiple things, right? And we're going to look at what it's made of. Because if it's made of more than one thing, you need to talk about the specific heat of the calorimeter and all of the components that are contained in a calorimeter. What does a calorimeter look like? So this is what it looks like, okay? This is known as a bomb calorimeter. It's got nothing to do with bombs, okay? Don't read that and be like, oh my God, this is a bomb. It's not a bomb, okay? Why do they call it a bomb calorimeter? It's because they're keeping the volume constant. And the idea is that whatever's happening in here, the volume isn't going to change. Okay, that's why they call it a quote-unquote bomb calorimeter, because it's a sealed container. You can't change the volume in it. Okay? And let's just kind of walk through what this calorimeter, how it all works. So, a bomb calorimeter is going to measure delta E for a reaction. Now, imagine the reaction is, I'm going to have my laser pointer. Imagine the reaction is right over here. Okay, here's your sample. And let's say this sample is going to undergo some sort of combustion, right? So a chemical reaction. We've seen combustion reactions like 1,000 times already. Imagine this sample is going to undergo a combustion reaction. And you guys know for combustion, you need some oxygen, right? So imagine this is some sort of sealed, tightly sealed bomb, quote unquote, where it's got your sample and there's oxygen in it, okay? And this sample is about to undergo a chemical reaction with the oxygen. How do you initiate a chemical reaction with the sample that's going to combust with oxygen? You guys see these wires over here? These wires are ignition wires. So, eventually you ignite the system and have it go through the wire, and eventually the ignition wire is going to ignite the sample, and it's going to start burning, and a chemical reaction is going to happen where you form CO2 and water, right? That's what a combustion reaction is you're making CO2 and water from some sort of carbon, hydrogen sample, right? It could also have oxygen. You guys have done combustion problems already where you calculated, how much carbon, hydrogen, oxygen. Remember, you guys calculated the empirical formula of this. Not that you have to really do that here. You just need to know that when you're burning a sample and having a combustion reaction happen, you're having a chemical reaction where you're forming CO2 and water. But that reaction is contained in this tightly sealed bomb. Okay? Now, what's going to happen? Well, all this stuff is going to burn and react and all of that. It's going to form CO2 and water. But obviously, from a combustion reaction, there's going to be heat generated, right? If you're burning a sample and you're combusting it, there's some heat that's going to be evolved in this tightly sealed bomb. But the volume of this tightly sealed bomb isn't going to change. So it's not like this is like a piston where it's moving back and forth or going up against an external pressure. It's staying put. The volume is going to stay constant. So the only way we can quantify the amount of energy that this reaction is going to happen in here, we can only quantify it in terms of heat and not work. Because if there's no change in volume, we can't calculate work. We can only calculate heat. Well, where's the heat going to go? The heat is going to go and increase the temperature of the water. And you guys see the water is surrounding this tightly sealed bomb. And notice there's a thermometer in here, right? It's going to track the temperature of the water changed after this sample is going to go through a chemical reaction. There's also a little stir here to stir the water, make sure everything's nice and uniform, the temperature is uniform. But this is basically what a bomb calorimeter is. And we can calculate the energy that's absorbed by the calorimeter, right? Q-cal, right? So Q subscript cal is just the heat from the calorimeter that the calorimeter absorbed from the reaction. That's going to equal to the specific, not specific, this is not specific, right? Remember, specific heat capacity is associated with like a particular substance, like water, aluminum, right? Heat capacity is different. It's not specific heat capacity. It's just regular heat capacity. So the Q-cal is equal to C-cal, which is just the heat capacity of the calorimeter. And as I said earlier, the calorimeter is made of multiple things. Right? The calorimeter is made of what? The water, the bomb, the container of the bomb itself, right? And remember, we're not trying to lose any heat to the surroundings, like any of the air that's outside of the setup of this bomb calorimeter. We don't want to lose any heat. We want all the heat to be absorbed by the water, right? But not just the water. The water isn't the only thing that's absorbing the heat. It's also the surface of this bomb calorimeter that's taking in the heat, right? Now, you might be wondering to yourself, how do you get the heat capacity of a calorimeter, right? Because we have a table of specific heat capacities for substances. How do you get the specific heat, how do you get the heat capacity for something that is made of multiple things, that, multiple things are absorbing heat? The water's absorbing the heat, the surface of the bomb calorimeter. How do you get that number? Well, it would have to be given to you. And there's a way to measure it experimentally, right? Imagine you were trying to get the heat capacity of a calorimeter. if you run a chemical reaction where you know how much heat is generated from it, so basically like, some sort of known reaction with a known amount of heat produced, you can figure out what the specific, I keep saying specific, you can figure out the heat capacity of the calorimeter by measuring the heat absorbed of something, how much heat it's going to absorb and release. You can calculate it. And then once you get that number, you can apply that heat capacity of the calorimeter to an unknown sample where you don't know how much heat it's going to release or absorb or anything like that, right? So that's how you can get that experimentally, but you wouldn't have to worry about it. It would be given to you, okay? So bottom line is the heat capacity of the calorimeter would be given to you. And the change in temperature is associated with the change in temperature of the water, right? So remember, the whole point of calorimetry is you're trying to observe a change in temperature of the surroundings. The surroundings. And you guys know the surroundings is the water and the bomb calorimeter itself, right? So with that in mind, if we know this is how we can calculate the heat absorbed by the calorimeter from the reaction that was run, right? This reaction produced a certain amount of heat, and the calorimeter absorbed that heat, and we can calculate how much heat was absorbed by the calorimeter from this reaction by equaling it to the heat capacity of the calorimeter times the change in temperature. But we also know that if no heat escapes from the calorimeter, the amount of heat gained by the calorimeter equals exactly the amount of heat released by the reaction. That makes sense, right? Anything this absorbs, this reaction had to lose, right? The reaction lost heat to the surroundings. If the reaction lost heat, it's got to be negative, right? Negative Q reaction. But realize that's equal to how much the calorimeter, how much heat the calorimeter absorbed, right? If something is absorbing heat, gaining heat, it's going to have a positive sign. You can kind of think of it like a checking account, right? Imagine, something is absorbing heat. That's like putting money into an account, right? Heat is being gained. You're adding money to an account. But something that's losing heat, that's kind of like a withdrawal, right? So withdrawal from a checking account kind of thing. You can think of it in many ways, but bottom line is we've seen this before, that if a system is losing heat, the surroundings is gaining the same amount of heat. Okay? Now, since the reaction occurs under conditions of constant volume, the volume isn't changing. That means that the Q of the reaction, the amount of heat released by the reaction, is equal to the amount of heat at constant volume, right? Because the volume isn't changing. And we said earlier that the change in internal energy of a reaction is equal to the heat at constant volume, because the work part is taken out. The work is equal to 0. So all of this is true. All of this is true. And you can go back on the other slide. We said this earlier, right? How delta E of a reaction is equal to QV, right? The heat at constant volume, which is also the Q of the reaction, okay? So this measured quantity is the change in internal energy of the reaction. So let's practice a problem associated with this. It says when 1.010 grams of sucrose, they told you the molecular formula of sucrose, undergoes combustion in a bomb calorimeter, the temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. Find delta E reaction for the combustion of sucrose in kilojoules per mole of sucrose. Notice the units. They want kilojoules per mole, right? We know energy is joules or kilojoules, but they want it over moles. So we're going to have to really pay attention to that. But one thing at a time for now. The heat capacity of the bomb calorimeter, determined in a separate experiment. I just told you guys what, they have to give that to you. And you can determine the heat capacity of a bomb calorimeter in a separate experiment where let's say you're burning a sample and you know how much heat it's producing, right? You can back calculate what the heat capacity is. But bottom line is they would give that to you in a problem, and they did. They told you what the heat capacity of the bomb calorimeter. 4.90 kilojoules per degree Celsius. Great. It also says you can ignore the heat capacity of the small sample of sucrose because it is negligible compared to the heat capacity of the calorimeter. Okay, so we don't need to worry about the heat capacity of the sample, just the calorimeter. Okay, so how do we solve this problem? Well, they told you it's a bomb calorimeter, and anytime you see the word bomb calorimeter, you think to yourself, oh yeah, the volume isn't changing. And if the volume isn't changing, you can't do any work if you're talking about pressure volume work. So the change in internal energy of the reaction can only equal Q at constant volume. And we know that this is going to be equal to the Q of the reaction as well. All right. And then, whatever amount of heat was, let's say, released by the calorimeter, right? This is a combustion reaction. We know that if the reaction is losing heat, negative Q reaction, the calorimeter is going to gain whatever heat was lost. All right. Now, we said what QCal is. QCal is equal to the heat capacity of the calorimeter times the change in temperature. And they told us what the heat capacity of the calorimeter is. It's 4.90 kilojoules per degree Celsius. So let's put that in. Times, times the change in temperature. They told us, so it went from 24.92 to 28.33. Let's put that in there. 28.33 is our final. 24.92 is our initial. Don't get that confused, by the way, okay? Don't say that the final temperature is 24.92, right? It's T final minus T initial. Final temperature minus initial temperature. The temperature rise, right? So you need to have a positive delta T here. Okay, so notice that now if I do a little bit of math, it's 4.90 kilojoules per degree Celsius. What's this come out to be? What is it, 3.41 when I do that subtraction? Right, I just did 28.33 minus 24.92, and I got 3.41. Notice the degrees Celsius cancels when I multiply the heat capacity and the delta T, and I'm supposed to get some number in kilojoules, right? So this is going to be 16.7 kilojoules is equal to QCal. All right. Now, remember what we said, though. We said that if we want to get the delta E for the reaction, we need the heat lost from the reaction. And notice it's negative of QCal. So if QCal is equal to negative Q reaction, well, then if I just multiply the negative for the entire equation, multiply the entire equation by negative, what do I get? I get negative QCal is equal to Q reaction. Right? The negative just distributes over. You guys know how to do that math, right? When negative distributes over an equation. So if I want to get Q reaction is equal to negative QCal. And that basically means if QCal is 16.7, I need to take the negative of that number to get the Q reaction, right? So Q reaction is equal to negative 16.7 kilojoules. All right, are we done? Because we calculated the Q reaction. But what did they want? they want the delta E of the reaction in kilojoules per mole, right? They said find delta E in kilojoules per mole. Right now we have kilojoules. So how do we get kilojoules over moles? Well, the problem told us how much sucrose reacted. They said that there was 1.010 grams of sucrose that reacted, okay, in this bomb calorimeter. And I don't think I need to say this anymore, but I know you guys know how to go from grams to moles, right? What do you need? The molar mass, right? So the molar mass, they didn't give us the molar mass, but they told us the molecular formula. So you can get the molar mass, right? What is the molar mass of sucrose? I think I got it over here. It's 342.3 grams of sucrose for 1 mole sucrose. All right, grams of sucrose cancel. And what are we left with here? I think I got a number, but whatever that number is, we know we need kilojoules per mole. So we got the mole part, right? This is going to be equal to some mole sucrose, some number. But we take that number and we want kilojoules per mole, right? So what that means is we need the kilojoule number, negative 16.7 kilojoules, divided by, right? Divided by whatever number moles. That's going to give us, I got the final, I didn't calculate the moles. You could do that, but you're supposed to get negative 5.66 times 10 to the 3 kilojoules per mole. That's going to be delta E of the reaction. Delta E of a reaction is typically reported in kilojoules per mole, because you're basically saying how much energy is available in 1 mole of that particular substance, so per mole, okay? That's typically how it's reported, but they would have to give you either the moles of the substance that's, being burned, or they would have to give you the mass, and you would have to get the moles from the molar mass, okay? But that's pretty much it for that. There are some practice problems related to this. So this is going to be on problem set 24. This is objective 12. So you'll find that problem set under objective 12. I'll post the answer keys for these as well, but I want you to give these a shot. Realize they're not that much different. Let's quickly read the problem. It says when you have 1.550 grams of liquid hexane, it undergoes combustion in a bomb calorimeter. Okay, as soon as you read the word bomb calorimeter, you're like, okay, constant volume, there's no work being done. It's all all the energy is released or absorbed in the form of heat. And notice they said the temperature rises from 25.87 to 38.13. So there's your delta T. They said find delta E for the reaction in kilojoules per mole of hexane, and the heat capacity of the bomb calorimeter determined in a separate experiment is 5.73 kilojoules per degree Celsius. Okay, so you have all the information you need to get delta E. And remember that it said kilojoule per mole. You just take the grams and divide it by moles. Take the grams, divide it by the molar mass to get moles. And then whatever your kilojoule answer is, divide by moles, and you should get your answer, okay? There is one additional practice problem that's going to be on the problem set. So notice in this problem, they gave you what the delta E is. In the previous 2 problems, you calculate delta E of the reaction. This time they gave it to you. But now what do they want from you? They gave you the mass of toluene that undergoes combustion in the bomb calorimeter. They told you the temperature rises from this much to this much. And they said find the heat capacity of the bomb calorimeter. Okay, so this is an example where you know how much energy is either absorbed or released by a reaction. You can take the temperature change and you can calculate the heat capacity of a bomb calorimeter given the right information. Okay, so try those on your own. Again, those problems are going to be on problem set 24. There'll probably be a couple more problems there that are going to be, we're going to work through that in the next video. So stay tuned for the next video. That's going to be talking about a different form of calorimetry. Okay, but this one is talking about bomb calorimetry. All right, thanks, and I'll see you in the next video.